In this video, we continue the Go systematic solution of the problems by using the equation of the appendix B in the BSL. If you want to remember the problem we deal here, we have a circular tube, and the length of the circular tube is L. This is the center of tube here, and the flow is going from down like this, and the radius of the tube is r, and we have some, so the flow is going the effect of the pressure and the other gravity forces. So in the problem is giving the postulate is the v is the only vz as the depend on rz, and vr here and v theta are equal to 0. So now we can go, if we go uh, okay, first start with the equation of the continuity for this problem. When we go the appendix B, actually appendix B, if we go the equation of the continuity, now we are in the for this problem we are in this problem the cylindrical coordinates, because we have the tube is r, theta, and z. In this problem, it's given the rho and the density and the mu, the viscosity, they are constant. That's why this term is going to be 0. Also, in this problem is given Vr is 0, V theta is 0. That's why this term also is going to be 0. And this term also is going to be 0. So we left here, rho is constant, then rho partial derivative Vz respect to z is going to be 0. Then we can obtain from here partial derivative Vz respect to z is going to be 0. So this is our solution of the equation of continuity. This show the change of the Vz in the direction of z is going to be 0. So Vz is not dependent on the z, only dependent on the r. So we obtain this result from the solution of the continuity equation. So in the first part, we just this problem we apply the equation of the continuity and we obtain this result. Now we move the second equation of motion. We have three direction r, theta, and z, and go and do the similar thing. And if you go again um, appendix B, equation of the motion, this equation is motion is for the cylindrical coordinate. This is the r direction here. So again, this term is going to be 0 because Vr is 0. This is going to be 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 0. In the right side, this at the same time the problems give, we have Rz and Zr defined like this minus d z over dr, because we know from the continuity equation Vz only the change respect to r. So from here, this term is viscous forces. R is going to be 0. Viscous forces is going to be 0. And this term is going to be 0 because viscous force Zr we have here, you see here, doesn't change respect to z, is only change respect to r. That's why it's going to be 0, 0, and this term is going to be 0. Finally, we obtain from our direction, left side is going to be 0, right side we obtain partial derivative of the pressure respect to r plus rho r. This rho is this term is going to be gravity and h, because we have circular tubes, flow is going under pressure, under effect of the pressure and the gravity. then we can write this plus rho g hash. Then we can combine these two terms. If you combine these two terms plus rho g hash is going to be big P. So we can write this equation minus partial derivative of big P is respective R. This result is in the R direction. You see from here. As we go from the solution, okay, the obtain the R equation of motion is going to be this. Now it's going to theta. If you do the similar thing for theta direction, in here is theta. This is 0 because v theta is 0. This is 0. This is 0. This is 0, and this is also going to be 0. On the right side, similarly, this term is going to be 0. This term is going to be 0. This term is going to be 0. This term, and left side from here, left side is 0. Right side 1 minus 1 over r partial derivative of p respect to t plus again, and and similarly we exchange same. This is, we can write this rho g hash theta hash, and this is going to be rho g hash, and we can write this, take this left, it's going to be 0 minus partial derivative big P is going to be P, big one is then T. So this is the result for the theta direction. We obtain that one 0. Similarly the R1. So in the, you see is similar. Now we are in the z direction. Okay, in the z direction. What if we go again the appendix B? Similar again the cylindrical coordinates in the z direction here. Okay, the we see only we obtain function of r, not the t and not the z. This is r. That's why this term is going to be 0. VR, because of VR, this term is going to be 0. V theta, this term is going to be 0. This term, because Vz, partial derivative of Vz, this is going to be 0 from the continuity of equation. At the right side, this term is 0, this term is 0. What we get from here, the left side is going to be 0. Right side, partial derivative z minus 1 over r so this rz plus rho. So again, if you combine this term together, these two, then we obtain minus partial derivative big P z minus 1 over r partial derivative of this r and rz. So these are result in the z direction. Okay, like here. Okay, what is going to be plus actually. Okay, if we exchange what, because we define uh, uh, rz is going to minus mu. If we apply here, then this mu is constant. We can take this out, and the minus sign is going to be the plus sign here. So this is final relation is going to be like this. Now, to obtain the velocity distribution with respect to r, we need to solve this equation. What you can see from this equation, we have in the partial derivative in the two directions z and r. The p is changing respect to z, and vz is changing respect to r, and left side is 0. there is only one condition we can obtain this term is 0. This uh, result of this term should be some constant minus c 0, and result this term should be some same c 0, and these two cancel each other, and then we obtain 0. Then if we set this 2 is equal to c1 c0 any constant number is arbitrary constant number, then if we take the integral of this first order ordinary differential equation, that one is give solution of that one. Is we have two constant z0 c0 and c1, the p equal that one. If we take 2 times integral of a derivative, sorry, this derivative of integral of that one is give that one, and 2 times integrate, if we 2 times integrate that one, we obtain vz equal to that one, and we have 3 unknown, 3 constant. Now in total we have in this solution we have 4 constants. These are c0 c1 c2 and c3. That's why we have 4 unknown. To solve this, to find these unknowns, we need to define for this problem 4 boundary condition. Again, the flow is going from the tube in this direction. The first boundary condition comes from the z is equal to 0. So this is the entrance of the tube. We have the p is equal to p0. The second boundary condition we set at the exit at the z is equal to L, we obtain P is equal to PL. So this second boundary condition. We are going to use these two boundary condition in this equation to solve the C0 and the C1. When the Z is equal to 0, then P is P0. That's why we obtain C1 P0. When the P is Z equal to L, P equals to PL, then C0, and this is going to be L. We know the C1 P0, that's why we can obtain the C0 from here, PL minus P0 divided by L. This is our second constant, and the first constant from here. Actually, if we continue our discussion, if we do the same thing for this, if we define the third boundary condition, this is the center of the tube, so this is the radius of the tube R. The third boundary condition, when the R is equal to R, we are in this corner. In this corner, the R is small r is equal to big R. Then our velocity is going to be vz 0 at this surface. You know that. For the fourth boundary condition, when the R is equal to 0 at the center, we have some finite vz. You know that. So then when we apply here this two boundary condition, we know what is z0. Then the solution of this equation is going to give that result actually. So these two results show the change of pressure respect to z when z change, start from the entrance to go to exit, how the pressures change. This Vz gives the velocity of the fluid when the R change. So we obtain here uh, parabolic velocity distribution because the velocity in the Vz direction on the function of R. So this is to obtain the velocity of this problem. So this is going to be, so from here is going to be the parabolic velocity distribution like this. So This example is our first example in chapter 3, how we use our continuity equations, and how we go and use the appendix B in the open form of the equation, and which terms we just omit and which terms we just keep while we are keeping, and what is the solution, and analyze all the problems. As a second problem, we are going to consider the flow of the fallen film. Let's consider the system, the entrance here, the exit here. The length of the flow is going to be L. The angle here is going to be beta. So this is the basic. We can consider this rectangular coordinates. Actually, here, this direction is going to be z, and this direction is going to be x here, that one. Let's consider this flow like this. Something is flowing like on the surface of this. This is the x direction. This is the y direct. The z direction, and this thickness of that flow. This is going to be our y direction. So again, when the z is equal to 0, the entrance, z is equal to L, is going to be exit. Y is equal to 0 is going to be here. Y is equal to W is going to be that thickness is going to be W. Okay, if you continue our discussion, when the big W and L compare the thickness uh, of that one, sorry, so in here we just define in different way. Okay, again, define again according to this problem, change our definition. This is, let's consider here some flow happening in here, and this is thickness of the flow, thickness like this. This flow is going here, this z direction. This is going to be y direction, and this is going to be just x direction, x. When this is actually w we represent, this y is equal to 0, and this y is equal to w, the thickness, and this the z is equal to 0, the z is equal to L, and the x is here. We see from x is equal to 0, this is thickness, we call x is equal to some thickness. So from that now, let's say we are the velocities vx and vy is going to be 0 according to definition of the problem, and we have some constant density. So for the solution of this problem, just we need to go appendix B1, appendix B1, uh, to check the continuity equation. So we are in here. This is our continuity equation actually here. So the problem says the rho is constant, that's why this term is going to be 0. Also our Vx and Vr is going to be 0. This term is 0, and this term, sorry, Vy, this term is going to be 0. We only get that term. If we take this, the rho is out because it's constant, then we obtain partial derivative of Vz, or z is going to be 0 from here, from this definition. And this is the solution of the continuity equation. So we have only Vz is change only respect x direction, because we see from here partial derivative of vz respect to z is 0, is 0. No, on our velocity on our system here, like here, when flowing this direction, our velocity only change in this direction, in the x direction here. It is not dependent on the z direction, that direction. Okay. Okay, this is the solution of our continuity equations. Okay. Now, if we go like problem statement here, now we need to find um, x, y, z type of solution of the problem, and we can say our viscous forces at the z direction, viscous forces at this z direction perpendicular to x is going to be equal to viscous forces at the x direction perpendicular to z direction is only going to be that term, because only vz is going to be dependent on the x. We found from the continuity equation dvz over dx is going to be 0. That's why we write just that term. So we have this viscous form, and keeping this mind, so then we go again the table to solve our uh, equation of the motion from here. Okay, now we are here in the rectangular Cartesian coordinate x y z for the this is the for the x direction, that one x1. Just go turn by turn. So the first one is going to be 0 because Vx is 0, Vx and the Vy is 0. It's going to be 0, it's going to be 0, it's going to be 0. At the right side, this we don't have any viscous xx0 and yx. Actually, this term is going to be 0. We have that term, but this term doesn't change respect to z, only change respect to x. That's why it's going to be 0. And finally, we get from here left side is going to be 0, and right side minus e over x plus rho gx. From here, we obtain that one. Keep this in mind. In the y direction, actually, this term is going to be 0, this term is 0, this is 0, this is 0. At the right side, again, this term is going to be yx, xy, this term is going to be 0, this term is going to be 0, this is 0, and in here, we obtain here left side is 0, right side partial derivative for pressure respect to y is plus rho y, a body force acting on the y direction. Came here the z direction. This time this term is 0 because it doesn't depend on the time, but this vx is 0, vy is 0, vz, partial derivative of vz is respect to z is 0 because of the continuity equation. At the right side, this is going to be 0, it's going to be 0. It's on the left, at the left side from here, 0. At the right side, minus p over z. This is going to be minus z, and this is going to be rho. So we obtain this three 3 form of the xyz direction by using the equation of motion in terms of viscous forces. So we go in the book. So what we get from that, we obtain in the first one that one actually that one. This was is the like raw, and we can write this raw gravity sine b, and we had at the right side here rho gy, but this term is because of the angle is going to be 0, then we left that one here. Finally we have here, we obtain again, we had rho, but we can write this rho gravity cosine beta, angle between plane and gravity. Let's call this beta. Then what we get from here, from here, so we just have this three uh, equations here, three equations here. So finally, from the continued equation and the equation of motion, we obtain these results that show pressure cannot be dependent on the y, and this also in here to get the how the actually the vz is functional x change. We need to solve this equation, but let's assume the pressure, partial pressure of the pressure respect to z doesn't change, is equal to atmospheric pressure. Then we can make this equal to 0. Then what we have then from here, and finally we obtain that form here. So we need to solve this equation now. Okay, let's go to solution. Let's go to solution. Okay, let's to solve that one. Let's integrate that equation. Then for the integration, we can have is equal to rho g cosine b x from the integration plus some constant. So we have just one equation and one constant, one unknown. So then we can set some boundary condition. So we can call this boundary condition 1. The boundary condition 1 at x is equal to 0. If you remember, our flow is going from here. We have some thickness here. We call this x. X is equal to 0. X is equal to thickness. When x is equal to 0, what's going to be condition? This term is going to be 0. Actually, what's this term? It's from here. So dvz over dx is going to be 0. So as a first boundary condition, when we put as a x is 0, then we obtain c c1 is as a 1. C1 is actually, let's call it c0, then c0 is going to be 0 from here to obtain this equal to 0. Okay, coming from that one. So then what's going to be our solution from here? Then this xz then is going to be equal rho cosine b. This is our result from here. Now in the second part, let's write the open form of this. What's this? It is going to be minus mu dv over dx. Then it's going to be rho g cosine b. Then we can write this from here. dvz over dx is going to be minus minus rho g cosine beta over mu. Then if we, as a next step, if we integrate that one, that equation we obtain with z, that is going to be minus rho g cosine beta is 2 mu x squared and c2. Now we have this equation. Now we need to find this c2 from this equation. Then we need to set second boundary condition. Boundary condition 2 is going to be run at x equal to the thickness. What was the thickness again in the flow? For the flow, we have some thickness of flow here in the x direction. X equals 0, x equal down. Then when the x equal to the thickness, then Vz also is going to be 0 from at the surface of the flow. Then when we put this here as a instead of here, that one is going to be that, and Vz is going to be 0 from this. Then we can obtain C2 from here. Then from solution of the equation, C2 is going to be rho g cosine beta to me, and the square is going to be that result actually. It's our C2. And finally, if we put all the things together, then our Vz was minus rho g cosine beta to me x square and c2. We found what was c, and if we insert c2 here, and we obtain this profile rho g cosine beta to mu, the 1 minus x over thickness of the film, than that. So this is the profile of the Vz in the z direction, how it's changing respect to x. And if we draw the plots Vz respect to x, then we obtain velocity distribution or velocity profile for this falling film. So this is going to be our velocity distribution from surface to from x equal to, actually in here in here is x equal to thickness, and this is the x equal to 0. So this is the solution of our problem. So Vz change respect to x, how it's change, and this is our momentum flux distribution here. That one is equal to mu dvz over dx. So sorry, what was this? This is going to be dx. So this is our momentum flux distribution of the fallen film actually. So this is our second problem in the chapter 3. So we will continue next video and by other chapters in the topic of the momentum transport. So see you in the next video.